So what we want to do with this video is work out the problems that we did in a large group class and have those for you as an archive, something you can look over if you were here and need to review them, or if you missed class, most importantly, that you have something to go back to and see what we did. So first of all, we talked briefly about the average atomic mass equation that we use to find average atomic mass, or as you'll see on the second problems in these examples, that we'll use to calculate these percentages abundance. So the average atomic mass is found based on the fact that all elements exist with more than one possible isotope, or more than one possible mass number, and that each of those mass numbers exists in different quantities. That's a fancy way of saying that out there in the world we have, for example, various elements coming in more than one possible form. We looked at this in class briefly, or something like it. We talked about it a bit in large group. The idea that, for example, carbon comes in three different forms by mass. One that's called a carbon-12, one that's called a carbon-13, one that's called a carbon-14. And the difference between each of those three forms isn't the protons or the electrons, which stay at 6 if we're talking about neutral atoms here, but it's those neutrons here that differ. As you increase the number of neutrons, you'll increase the mass number, and the name goes with it, carbon-12, 13, and 14. The reason we need to be able to find average atomic mass is because, in reality, the amount of each isotope of those three, for example, in carbon, aren't found in equal amounts. In other words, there's not 1/3 carbon-12s, 1/3 carbon-13, 1/3 carbon-14. There's several different kinds, and they're all in different proportions. So it's not going to be even. If there are just two isotopes, like in the example that you'll see in this equation here, first isotope, second isotope, if there were simply 50% of the first isotope and 50% the second, then the average would be simply halfway in between the two. But as we go look at the problems that you'll see in the examples, the isotopes don't come in 50-50 percentages or in 1/3 of each of the three different isotopes and so on. You'll see that the percentages are seemingly very, very random, and that we use this equation then to find the average atomic mass. So as we go through the problems, you'll see us use this equation in its various forms to solve each one of the problems in front of us. So let's get started and jump in on a problem. This is the side, one of the two sides on the sheet that was handed out and used in large group. And this is the page, the problems that we'll work through here in the videos as well. So we did questions 5 and 6 on this side of your page, and then on the other side we'll work through questions 1 and 2. Question 5 says that the two isotopes of iridium are listed below, each with its percent abundance and the composition of its nucleus. Using these data, calculate the average atomic mass of iridium. So if we look at iridium, you can see both of these nuclei, these are just the nucleus of the atom of iridium, have 77 protons apiece. So iridium has an atomic number of 77, and you can find it there on your periodic table. Each of these two have a difference, though, in the number of neutrons. You can see this one has 114 neutrons, this one has 116 neutrons. That difference in mass, then, as a result, is what we're looking for in calling these two different isotopes of iridium. The first thing we want to do here is add these together because we need the mass number. We need the total mass of each of these. So if we add 77 and 114 together, we would call this iridium 191. Just adding these two numbers together, 191 AMUs, and we'd call that iridium 191. And over here, we add these together and we get 193. So this is then simply iridium 193. Now to find the average atomic mass, which is the question that we're being asked to find here, to find the average atomic mass, we simply use the equation that I just showed you. And again, that was this. The average atomic mass is found by taking the mass of the first isotope times its percent abundance written as a decimal, plus the mass of the second isotope times its percent abundance written as a decimal. So we'll use that equation. Average atomic mass, and I'll just abbreviate it as AAM, is the mass of the first isotope, which is here, 191 AMUs. And I'll leave the AMU off because everything's going to be in AMUs here, and it'll help keep it a little bit cleaner for these first examples, times its percent abundance written as a decimal. Well, its percent abundance is here, 37.30%. To write any percentage as a decimal, you simply divide it by 100, or some people think about it as move the decimal 2 places to the left. Think about this way. If something was 75% of the isotopes, to write 75% as a decimal, you would write it as 0.75. You move the decimal point 2 to the left. And the same thing if it were 50%, we'd call it 0.5 or 0.50. So in this example, 37.30% written as a decimal is 0.3730. The second isotope, its mass is right here. We just figured it out to be 193. So the second isotope's mass, 193, times its percent abundance written as a decimal. And again, we're given that information here, 0.6270 when we write it as a decimal. Okay? Now, to calculate that, to go ahead and find the answer, we just pull out our calculator, punch those in, and add it all up. And you can do that in one big calculation in your calculator. You could find the answer for each half. You could find the answer for this half of the calculation, and then again this half of the calculation, and then you could add those two together, or you could punch the whole thing in at once. I don't mind if you punch it in all at once. We haven't gotten too far at this point in the year. We haven't started talking about rounding rules and that kind of thing just yet. So whether you punch it in all at once or do it in two parts, the rounding rules aren't something we've discussed too much. So you'll probably get the same answer either way. And when you add these up and get the big total at the end, you're going to get an answer of 192.2 AMUs, 192.2. And if you take a look at your periodic table, you should find that the average atomic mass for the element iridium at atomic number 77 comes up awfully close to 192.2. So that's the average atomic mass. Now we just want to emphasize that when we say average atomic mass, we're saying that of all the iridiums out there in the world, that the average iridium atom has a mass of 192.2. There is no iridium atom with that mass actually being 192.2. That's the average of them all. And like Mr. Mitchell made the good example of in large group, if we ask you how many girls are in the average class at Legacy High School, you might say 13.7. But you're not going to be able to find 13.7 girls in any class because people don't come in fractions of a whole. And so as we look at our problems here, we're coming up with an average that represents the average iridium atom out there and its mass, but there is no such atom with that actual mass. It's the average of many, many atoms all put together. So those averages are going to be fractions or decimal answers, even though the single atoms, as we look at them here, have whole number masses, 193 and 191, whole number masses. And the averages generally won't be a whole number. All right, let's look at another example. This one's for potassium, and this one's got three forms, or three different isotopes. We've got a potassium with a mass of 39 AMUs. We've got a potassium with a mass of, if we add this up, 40 AMUs. And again, we're just simply adding protons plus neutrons to get the mass number. And here, the heaviest one, 19 plus 22, 41 AMUs. Again, notice each of these isotopes has 19 protons in it. And that makes it a potassium atom, but the number of neutrons is changing from 20 to 21 to 22. The atoms are getting heavier as we have them arranged here, and those mass numbers are increasing from 39 to 40 to 41. So to find the average atomic mass, I'll work it out just below here since we've got room. The average atomic mass is the mass of the first isotope, which is 39 AMUs, times its percent abundance written as a decimal. So I'm going to move that decimal point over 2 again and get 0.9326 plus the mass of the second isotope, 40 in this problem, times its percent abundance written as a decimal. Now this is the one that usually causes the most confusion because I seem to have already got some zeros showing up here, and often students will look at that and think, I don't need to move the decimal point over since it's already kind of a small looking answer. But you do. Because it's a percentage, we still need to move it over 2 decimal points or places to get the number that we want here. Oops. And so our value then becomes a lot of zeros here, 0.000117. It's a very small answer, but even if this is a small percentage, you need to move that decimal point over twice in order to turn it into a percentage written as a decimal, and that's what our equation says, remember. So we've got a third isotope here, 39, 40, 41. Keep in mind our general equation for the average atomic mass that we keep referring back to here has a ... at the end, which means there can be as many isotopes as you like. In fact, there are atoms that have, or elements that have 7, 8, 9 different isotopes. So this could get really ridiculous. We won't give you any quite that long, but they could get pretty lengthy in lots of these problems. Our third isotope then is 41 AMUs, and its percent abundance, again written as a decimal. Carefully, I'm going to move that over twice, and I need to put one more zero there. So when I write 6.73% as a decimal, it's 0.0673. Okay, so there are my three isotopes. Potassium 39 here first, potassium 40, and potassium 41. And when we add all that up, we get our final answer. Now, before we put that up here, or before you go punching it in if you haven't already done that, look at the balance that we have here. The balance, we've got tons and tons. Almost all of them are these potassium 39s, 93%. That's like almost the whole pie chart, if you think about these as a pie chart. We've got about 6 or 7% that are a potassium 41. That's not very much compared to 93%, but there's some there. And then there's this teeny tiny percentage of those that are potassium 40, hardly any at all. So if you think about it, the average should be very close to the isotope that has the most kind of proportion or share of all the atoms of potassium out there. So as we get an average, be thinking about that. Is my answer realistic? Is it logical? And in this case, if I add this all up, I get an answer of around 39.14 AMUs. So my hypothesis there, or my kind of prediction, makes sense, or was correct, in that the average, 39.14, was really close to that dominant isotope that was potassium 39, and not very much higher. Even though there was some 41s, because there were so many potassium 39s, the average stays quite low, near 39. So for these two examples, again, we had two, now three. Our first one had just 2 isotopes for our iridium, and our second one has 3. As you go further down the page, you'll find lead and chromium in these problems that have 4 isotopes apiece. We just keep adding mass times percent, mass times percent, mass times percent, as many as you need. And those last problems, you'll need 4. So we'll leave those 2 to you. Now, let's look at the other side of the page and take a look at some problems from the back, or depending on how you look at it, could be the front. So on this side of the page, we've got the other kind of average atomic mass problem. And the other kind is the sort where we're not finding the average like we did on these last ones. We've been finding this average atomic mass on the first side on questions 5 through 8. Okay, we were finding the average atomic mass. And we don't need to do that on questions 1 through 4. So on that side, I'm going to just clear that back off again. On that side, we're going to have the average atomic mass actually being given to us already. And they're going to ask me to find the percent abundance. This is going to be what I'm looking to find, the percent abundance of each of these. And we don't know either one. Now, remember, on the other side, we had some problems where we had to solve for as many as 3 or 4 different atoms here. On the other side of the page, questions 1 through 4, there are just 2 isotopes on each of them. And for our example equation here, or kind of our standard equation, looking for the percentage abundance, this part here, on each of them. We're going to have the average given to us, and we're going to have the mass of each of those 2 isotopes given to us as well. So let's take a look at this equation and see if we can figure out how to set this thing up. Right out of the gate here, it tells me the average atomic mass of gallium is 69.723 AMUs. Now, again, that's this, right? That's the average atomic mass. He just gave it to me. I already know it. So I'm going to go ahead and put that into my equation as 69.723 AMUs. And again, I'll leave AMUs off just for keeping it a little tidier on our example equations. If I already know the average atomic mass, what else do they give me? Well, in the problem it says this gallium is composed of 2 isotopes, gallium-69 and gallium-71. So here are my 2 masses, gallium-69 and gallium-71. Those are my 2 different isotopes of gallium. So I know I've got a gallium-69. And I don't know its percent yet, so let's hold off on that. Plus a gallium-71. And again, I don't know its percent either. All right. So again, thinking about my kind of general equation here, I'm just going to clear this stuff off so we got a little bit tidier space up for us to work here. Okay. Whoa, didn't mean to take the whole thing. That's not going to work. Let's try that again. All right. So on our equation, I know the masses and I don't know the percents. This percent is my unknown, my first unknown, this guy, and my second unknown is the other percent. I don't know what these are. Now, what I want to point out to you before we go solving this problem is that if I know one of these, I know the other. And the way to think about that is, let's say if this is 75% written as a decimal, that would be 0.75. Then I know that this has to be 25%, or written as a decimal, 0.25. Now, they're not always going to be 75 and 25, of course. We just did some examples where it was other things. So let's say, for example, this first one is 0.63 or 63%. Well, then I know the second one would have to be 0.37 or 37%. The percentages, 63% and 37% have to add up to 100, no matter what they are. And when I add up the decimals, written as a decimal, they have to add up to 1, or we could think about it as 1.00. So writing it as a percentage, they add up to 100%, which makes sense. And writing them as decimals, they have to add up to 1, which is 100% written as a decimal. So what I want to point out to you about all that is, no matter what, if this is my x, if I call this x, and our tendency is to call our first unknown x, if this is x, then this is the rest of whatever adds up to 1 or 100%. Now, we're going to write them as decimals, so let's concentrate on this column right here. Right? If x is my first one, this first value here, then the other value, this one, is whatever it takes to get a total of 1. In other words, this is 1 minus x. A lot of people will be tempted to call this first one up here x and the second one y, and that's relevant. That's fine. But no matter what, x and 1 minus x have to add up to 1. So again, if this is 0.75 on the top, then this is 1 minus 0.75. So if this was 0.63, then this is 1 minus 0.63. And that's how we got our 0.37. So these percentages and these decimals are two different unknowns, but we do know something important about them, and that is that they have to add up to 1. No matter what the first one is, the second one has to make it possible for the two of them to add up to a total of 1 when we write them as a decimal. So let's plug those numbers in here and see if we can set this thing up and get it solved. Let's call this first one x, because we don't know what it is, and we like x. And the second one, instead of calling it y, we're going to say is 1 minus x. Whatever these two percentages are, we don't know what they are yet, but whatever they are, they have to add up to 100%, or since we're writing them as a decimal in our equation here, written as a decimal, we're going to see them as adding up to 1. So x and 1 minus x in those two percentage positions, written as decimals. Now, let's go ahead and solve for x here. We're going to get the equation manipulated and cleared around, moved around here to get x by itself, right? When we solve for x, that's kind of our goal. And so the first thing I want to do is distribute. I'm going to distribute this 71 out to both 1 and negative x. So I'm just going to carefully kind of go through this problem and rewrite it for you. 69.723 is equal to 69 times x. So I'm just going to get rid of those parentheses and call that 69x. And then over here, I'm going to go ahead and distribute my 71. So 71 times 1 is 71. That's not hard math. And 71 times a negative x is negative 71x. So all I've done so far is distributed, right? Now, if I ask students, what should we do next? They're going to usually say group like terms. And I'm with you. Let's go ahead and group like terms. So if we put the 69x and a negative 71x together, what do we have? Well, we have negative 2x. If we put those together. The other thing we want to do sort of at the same time here, and I'm going to go ahead and do it in a different color, but I want to do it at the same time here, is I'm going to subtract 71 from both sides. I'm trying to get all the x's on the right, and I'm trying to get all the numbers essentially on the left, right? Let me line that up just a little bit better, since I didn't do a very good job of doing that the first time here. Let's go ahead and line that up a little bit better. Take away my 71 over here, and what's left? Well, 69 minus 69.723 should be 723. 69.723 minus 71 is a negative 1.277. I get a negative answer, of course, because I subtracted a smaller number minus a larger number. Now, negative 1.277 equals negative 2x. So how do I get the x by itself? Well, divide both sides by negative 2. And I'll have x by itself on the right side because these will cancel out, right? And so x here will be, and check my notes real quick, 63.85, so 0.6385. Now, don't forget, in math class, maybe you get to the end and say, I solved for x, I found it, got the answer for x. But in this, we're using it to describe something specific. And so when that's the case, what does x mean? Well, let's go back up to the top of the problem. Here, x was the percent of this isotope written as a decimal. Remember, x here is the percentage of our gallium-69 written as a decimal. So what we need to do is take this percentage written as a decimal, 0.6385, and turn it back into a percent. So to do that, we move the decimal back to the other way, and we get this to be 63.85%. Now hopefully that makes sense, turning a decimal into a percentage. But 63.85% is the same as 0.6385. And so 63.85% of our gallium is, remember, these go together up here, 69 and X go together. So 63.85% are gallium-69 atoms. And the other ones here, 1 minus X, would be our gallium-71. Now how much is 1 minus X in this case? Well, 1 minus X is 1 minus 0.6385. Remember that was our X. So that's 0.3615. Or, again, written as a percentage, 36.15%. Remember, our percentages have to add up to 100, and they do. So it adds up perfectly to 100. Gallium-69 is 63.85% of the isotopes, and gallium-71 would be the other 36.15% of the isotopes. And think about it, the average is a little bit closer to 69 than it is to 71 here. Our original average, way up at the beginning of the problem, was 69.723. A little bit closer to 69 than to 71. So in the end, we should have more gallium-69s than we do gallium-71s. And sure enough, we do, 63 to 36%. And so it kind of works out. Should kind of have some logical sense to it too. Now, that's pretty much just algebra, right? We figured out that X and 1 minus X were the way we set up our problem. And once we do that, the rest of it's just basically rearranging the equation. We distributed, we got the X's grouped together on one side of the equation, and then got the X by itself, and boom, turn it back into percentages, and we were done. Let's go through number 2 real quick. You still have another example in your pocket. If you think you get it, go ahead and solve the whole thing. Pause this video, solve number 2, and see if you get it correct. And if you do, you can fast forward to the end and find out if you did. And if you did, great, go ahead and do 3 and 4. If you'd like to work through this one with us, feel free to do that step by step. And if you'd like to try it by yourself and then come back, hey, if you made mistakes, then play it out and see how you did. So if you need to pause me now. Okay, either you didn't pause me or you're back. So let's go ahead and plug this stuff in the same way we did our first example and see if we can't get some answers. The average atomic mass of antimony is 121.760. So that's our starting number, 121.760. There are 2 isotopes of antimony, 121 and 123. Those are our 2 mass numbers for our 2 isotopes of antimony. 121 and 123. All right, so just like the last problem, we're going to treat these as the 2 values we don't know, these percent abundances. What is the relative abundance of the isotopes, or what we should say, what are the relative abundances of these isotopes? Well, we're going to do the same as we did last time, X and 1 minus X. If you get sick of working with X's, go ahead and use Z's or P's or Q's, I don't care. So go ahead now and solve for X, right? So we're going to work these processes out the same way we did in the last one. So I'll go ahead and do that. 121.760 is equal to 121X on the right side, plus, again on the right side, 123 times 1 is a positive 123, and 123 times a negative X, don't miss that negative, is negative 123X. This isn't such hard math, even if you don't think you're a real solid math person. So let's get the X's together. If I put my X's together, these and these together, combine those together, I'm going to go ahead and just do that right over here. Negative 2X. Okay, and group those together. Now I'm also going to go ahead and subtract my 123 from both sides. So to do that equally on both sides here, and then we'll have our next line. So that's gone on the right side, and over here, as we saw in the first problem, we're going to have a negative answer. Negative 1.240. We're almost done, right? Divide both sides by negative 2. And you'll have X equals 0.620. Now what is that? Again, that's a percent abundance written as a decimal. So 1.240 divided by 2 gave us our 0.620, which represents 62%. Right? In fact, it's exactly 62%. But what is it? 62% X was with this isotope, antimony 121. So that's this guy right up here. 62% are antimony 121, and the rest are antimony 123. Now again, you could take this as the rest from this guy being 1 minus 0.620, which would be 0.380, or 38%. You can do that if you want. I think most students start figuring out that it's a little bit easier just to go ahead and subtract the percentage I know, which is 62%. Subtract that from 100. Now it's up to you. But as long as those percentages add up to 100, you don't even have to really bother with all this business here, as long as you can just subtract the first percentage that you solve for from 100. And the other isotope's mass from my original given problem text up here was antimony 123. All right. Again, well, does it make sense? Does it fit the data that we had? Well, sure. The average is 121.760, which is a little bit closer to 121 than it is to 123, and so we should have more 121s than 123s, and we do, 62 to 38%. Now, both of these were in that 60-something to 30-something percentage range. They're not always going to work out that way. In fact, there are plenty of elements whose isotopes are very, very lopsided, like 90-something percent and like some single digits, 5% or something. There are also those that are very, very close to 50-50. So it could really be anything along that spectrum as we solve for these problems. The other two that are left on this page are very, very much like those first two. So go ahead and solve for indium and rubidium on questions 3 and 4. We had asked you in large group, this year anyway, to solve for the other problems that were left on the sheet. So 3 and 4 on this side of the page, and on the other side 7 and 8. Before we see you in your next small group class this coming week, which would be the week of the 12th through the 16th. We hope to see you then with problems in hand. If you have questions and have a chance to see us before then, stop in on a Saber time or catch us outside of class. Otherwise, we'll take your questions in class. See you then.